Please welcome Dongara Professor of High Performance Computing at the University of Tennessee at Knoxville, Michaela Toffler.
Good morning, everyone. Good morning. My name is Michaela Taufer. I'm a Dongara Professor in High Performance Computing at the University of Tennessee, Knoxville. And I'm also chairing the invited talk of this session with the title Computer Industry Innovations in HPC. It is an absolute pleasure to introduce today our first invited speaker of this session, Dr. Pavan Balaji, who is a renowned leader in the field of AI and HPC system. Dr. Balaji is a principal research scientist at Meta AI, where he leads effort in two critical areas, GPU training system and AI communication library across Meta diverse hardware platforms. He has been instrumental in building some of the Meta most advanced AI supercomputing system, including the groundbreaking Grand Titan architecture, which powers state-of-the-art workload like recommendation models and generative AI models, including Llama. Before joining Meta, Dr. Balaji served as a senior computer scientist and group lead at Argonne National Laboratory, where he works on revolutionary communication runtime system, trading model, and heterogeneous memory system. His contribution to projects like MPEACH, UCX, and ArgoBots have had an enduring impact during driving innovation across supercomputer and commercial platforms, including the current generation of US exascale supercomputer. Please join me in welcoming Dr. Pavan Balaji to share his insight into the future of AI and HPC at scale. Dr. Balaji, Pavan, the floor is yours.
Right. Thank you, Michaela, for the kind introduction. Thank you for having me here. It's my honor to be presenting this talk over here on the infrastructure, Meta's infrastructure for generative AI models such as Llama. This work was, of course, not done by me alone. There are hundreds of researchers at Meta, maybe thousands, depending on how you count, who have been working on this. It is my honor to represent them for this talk. Okay, so I'm going to start off with a short video. It's a little bit of a cheesy video to kind of give an idea of how our infrastructure looks like and where we are building towards for these generative AI models. Okay, so maybe you can play the video.
Infrastructure fundamentally is what I call the engine behind the growth of this company. We have been building data centers since 2010. We're talking about serving maybe a half of humanity. Now, when we're talking about AI, you need a similar engine behind AI so that AI can achieve the potential that we are sort of dreaming.
AI workloads are growing at a pace of 1,000x every 2 years. I mean, just contemplating what that means for our systems, our silicon, our software stack, we're in the middle of a pivot to the next age of information.
The models themselves are becoming hundreds or thousands of times larger and more complex. And what this is going to require is infrastructure at the exaflop level.
We're reimagining everything we do about our infrastructure for AI. We're creating data centers that are specific for AI. We're creating new hardware, including our own silicon. We're building out new kinds of network architectures. We're reimagining the software stack like PyTorch. Thousands of engineers are innovating on this large-scale infrastructure that's built specifically for AI.
All right, that was my cheesy video. Let's move on to the content. As I mentioned, this talk is about generative AI, but AI at Meta itself is not new. We've been doing AI for a few years now. Generative AI, on the other hand, that's fairly new. We started 2 or 3 years ago working on these generative AI models. These are models that to create new realistic content for the users. That could be text content, image content, videos, and so on and so forth. We started that a couple of years ago. We released the first version of Llama in 2022, followed by Llama 2 last year. And of course, earlier this year, we released two batches of Llama 3 models. The first batch was the smaller models with 8 billion and 70 billion parameters. And later, we released a larger model with 405 billion parameters. The larger model for Llama 3 today is the largest dense production model that's available today. That's used in production, it's a dense model. It's not a MOE sort of architecture, but it's one of the largest models out there. It is a fully open model that is very competitive with most flagship competitor closed models that are out there in the industry. The picture on the right shows some of our competitive benchmarks, how it compares against the competition. And you can see that this is a flagship model, a frontier model that is competitive across a wide range of domain areas with the top of line models across the industry. Now, Llama itself is just a mathematical model. That's what sits in the back end. But to interact with Llama, you need to use some form of a product. Meta AI is one such product. It is integrated into the Facebook or Meta family of apps, such as Facebook, Instagram, WhatsApp, and so on and so forth, where you get a small prompt where it allows the user to interact with Llama in the back end, either through text conversation or image generation or video generation and so on. You can see a picture of Zuck on the top over there, announcing this earlier this year. Okay, so that's with respect to the model itself. Now, the quality of the model is a very important part of doing this work. Okay, so there's a prompt on the top. This is the image generation part of the model. The prompt on the top is constant. That's a prompt that says, I need to generate an image of a pug in a superhero costume with so and so requirements. Okay. The left picture over here, that's the model, that was the image that was generated with the early generation of Llama series models. Okay. The picture is fine, but it's a bit cartoonish in the way it is created. It's not very realistic in that sense. That's 2022. Fast forward to June 2023, the exact same prompt, you can see that the quality of the image is much better. It's much more realistic. The colors are more vibrant and so on, which makes the perception of the model, the quality of the model much better compared with where we were in 2022. That's with Llama 2. And of course, fast forward to this year, we have Llama 3. And this is a much more better model compared to Llama 2. It has improved accuracy through using, of course, a much larger model size, much larger number of parameters, but also a lot more high quality data that backs these models. Now, one of the things that we spent a lot of time doing in Llama 3 was improving both quality and speed. These two are very strong duals. Okay? You can get very high quality by making a very large model, but in doing so, you make it very hard to serve it fast. Okay? Very large models take a long time to serve fast. That's where infrastructure, that's where HPC comes into play. We want both of them. We want, of course, very high quality models, a lot of parameters, but at the same time, we want to be able to serve them fast, and that's why we use very large supercomputers with a lot of GPUs with a very fast interconnect, connecting them with very fast storage and so on and so forth. Let's see, the picture on the right are just showing the different apps that we use. Okay, I'm going to focus the rest of the talk on the training part of our system. I'm not going to talk a lot about serving inference, but we can chat offline if you're interested in that. I'll be focusing on 4 aspects of training in this talk. The first one is, of course, the compute systems that we used for our training. The second one is the data that we used, a little bit about the data. Third, I'll talk about the network infrastructure, and finally about the software stack that we used to train the Llama models. Okay, talking about the compute part. First is we used a GPU-based system, a GPU-based supercomputer to do this. Meta has a lot of GPUs that we used. AI is a significant part of our infrastructure, and a large part of AI runs on GPU-based systems. We have a very large portfolio of different types of accelerators to support our AI workloads. For example, we have almost 350,000 H100 GPUs in our fleet, And plus we have other GPUs, like we have A100 GPUs, we have AMD GPUs, we have our own internal silicon and so on. Aggregate all of them, we have an equivalent of 600,000 H100 GPUs that are used across a wide range of AI products. Of course, it's used for Llama, it's used for our recommendation models, it's used for training, it's used for serving, and so on and so forth. So it covers the whole spectrum of our AI workloads, but that's the size of the portfolio that we are maintaining for our AI infrastructure. Now that's basically the GPUs themselves, but the GPUs themselves are not useful unless we plug them into a large supercomputer. Okay, that's where the Grand Teton supercomputing architecture comes into play. Grand Teton is the architecture. It's been open sourced, the connectivity and how the architecture looks like a couple of years ago at OCP. Just as a brief, like a top level update of how this looks like, it is a bunch of racks. Each rack has a couple of nodes. Each node has CPUs. It has 8 H100 GPUs. It has NVLink switches to connect them. Each GPU has a dedicated back-end NIC with 400 gigabits connected at the back, and a bunch of front-end NICs, and so on and so forth. And we take 2 of these nodes. That's one node with 8 GPUs. We take 2 of these nodes, put it in a rack, so 16 GPUs per rack, and then we connect a bunch of these racks together to form the full supercomputer. Some section of these racks have full bisection bandwidth, some of them are tapered. I'll talk a little bit more about that in the later slides. That's the overall supercomputing architecture that we used for training Llama. So a little more specific details about the training architecture itself. We used 2 supercomputers to train Llama 3. Each one of them was 24,000 H100 GPU supercomputers, and an aggregate of 200 exaflops of FP8 performance. This is a 2-to-1 sparsity. Both supercomputers were based on the Grand Teton architecture, with the primary difference that one supercomputer was based on InfiniBand, the other supercomputer was based on Rocky. Other than that, basically the 2 supercomputers were identical. And we trained parts of the model on one, parts of the model on other. They both performed fine. There was no, practically there was no big difference between these 2 supercomputers. There were comparable performance between the 2. But these are very large supercomputers, and the training itself ran for a long time, several months on these supercomputers to get to a point where we had a pre-trained model. Again, we followed that up with additional post-training / fine-tuning to get to the final models that were released to the public. That's with respect to the compute architecture itself. Let's take a minute to talk about the data and storage. Okay, there you go. So data and storage. So compute, other than compute, data and storage also play a very critical role in the overall training system. This is usually not talked about as much. People talk about, we use so much compute, we use so many parameters, and so on and so forth, which is very important, of course. But data is equally, if not more important than the number of parameters or number of GPUs themselves. We need a lot of data, of course, but together with the volume of the data, we need high quality data. The quality of the data has to be good. We can't have noisy data. We can't have data that is repetitive and so on if we need to train a very high quality model. I think this particular information was, might have seen in press releases. Llama 3 used 15 trillion tokens of data for our overall training, which is more than 7x more than Llama 2. Llama 2 only used like 2 trillion tokens of data. This is not the largest amount of data that is used in the market. There are other models that have used even more tokens of data, up to 40 trillions of tokens of data. But like, as I said, it's not just the volume of data that's important. It's also the quality of the data that's very important for our training part. Together with the data itself, there's also the storage infrastructure that backs this data. We used a flash-based storage system. I'll talk more about that, based on our own internal distributed file system called Tectonic FS. Now, a little more detail about the data. This part is, of course, a part of the press releases. So you should have seen this perhaps in the press announcements. We used 15 trillion tokens of data. But I want to go one step deeper to explain a little more about the data itself. The TLDR at the top level is that because at 15 trillion tokens, the amount of data is so large that it's beyond what humans can do with curation. We have to look at automated tools to be able to curate this data, to augment this data, to improve the quality of the data. And because it's so much amount of data, we used Llama to curate the data and amend the data while training Llama. So we used Llama 2 or smaller versions of Llama 3 to curate the data for the frontier model of Llama 3. I'll talk a little bit about that. Okay, so let's see, my clicker is not misbehaving a little bit. So we used multilingual data. So Llama 2 was all based on English. For Llama 3, we moved to multilingual data. We supported a bunch of additional languages and continue to add more languages for Llama 3. This required us to increase our vocabulary size to 128,000 elements. That's a pretty large vocabulary size, among the largest vocabularies that any frontier training model has used so far. Then on top of that, we had significant major data quality investments. So we used, for example, for web docs, we used something called as a Wikipedia reference score. This essentially says that we use Wikipedia as a way to say there is some form of a human review on the documents. It's not just random web pages that we are picking up, but what is the probability of the document to be referenced by Wikipedia? What's the probability of a document to be reviewed by a human or a collection of humans for accuracy before we can use for our training? So we use something called as a Wikipedia reference score to get to that point. We also used Llama 2, the previous generation of Llama, to do some quality filtering. So Llama 2 would look at the data, would assess the quality of the document, and prune out low quality data. So our Llama 3 training can use only high quality data for the training. So we did this using the previous generations of data. One catch I should mention is that we can't 100% automate this, because if accidentally we introduced a bias in Llama 2, we don't want that bias to propagate forward to Llama 3. So we want to have some level of human involvement to kind of audit the filtration that Llama 2 is doing so that we can get really high quality data for Llama 3. Then, okay. We also added a lot of more code and math, reasoning, generally problem-solving content into our data set. We had to do a lot of work to kind of extract and process this sort of data to augment the data. This sort of data is not readily available very easily on the web. So we had to use other external sources, like for example, coding competitions out there, get license data from that, be able to train the model a little better with more high quality data that has been reviewed by others. And of course, we used synthetic data as well for our models because I'll talk more about this, but human created data is kind of coming to an end. So we used what is called as rejection sampling approach, which uses, essentially creates unit tests and executes these unit tests. And we use that as a feedback loop to see what kind of unit tests, what kind of code is high quality code, what kind of code is not high quality code. So we use this feedback loop to create tests, execute them, make sure they are running fine, and then feed that into the training of the Llama models. And finally, we used a variety of data sources. We used web documents, we used like dialogue, code, and so on and so forth. And across a wide spectrum of areas, we used like world knowledge, we used art, we used math, coding, and so on and so forth. We had to work around this a little bit because it turns out that on the internet, there's a lot of art content, but there's very little math content. So we had to do some work to kind of augment that and make it a little more balanced across these different areas. And finally, we use these models both for training. Of course, that part is obvious. We have to use this for training. But we also use it for serving or inference, because when there's a query, we need to be able to index and retrieve this data that we use for training to be able to serve users with the appropriate content. So we use it both for training and for serving for our systems, for Llama 3. Okay, so looking at the data life cycle of this, so of course, there are multiple steps. There's data selection, what data sources we use, and how do we get the data content. There is mitigations. Meta has several privacy rules that we use. So we want to make sure that there's no, for example, PII, personally personal identifiable information in the content. There's no adult content in this data that we are using, or anything that doesn't meet the Meta's privacy regulations in this content that we have to kind of get rid of. Again, as I mentioned, we use automation techniques to identify, for example, what language this document is written in, or what the topic of the classification is. So we used either previous generation Llama, like Llama 2, or a smaller version of Llama 3 to do this quality assessment or this classification before training the full Llama 3 model. And of course, we filter out, we do additional curation to filter out low quality content. I talked about that in the previous slide. And do upsampling, downsampling, also as I mentioned. Upsampling for content that is very little, such as math, and downsampling for content that is a lot, like art. Okay, that's with respect to the data itself. Let's take a step back and look at the storage system. This is the piece of hardware or software that is hosting our data. And at a very high level, it's a very simplistic model, right? A training system is an iterative loop, very much like scientific computing. We have a starting point where our parameters are initialized to some preconditioned values or perhaps random values. We ingest a bunch of data, we train it, once in a while we checkpoint the data, and we keep iterating over this over and over again for many, many iterations, and finally we come up with a final set of parameters. The data ingestion is, of course, all reading the data from the file system, and the checkpointing is saving the data to the file system. There are the sizes on the slide over here if you're interested, how much data we are saving per GPU. Now, the big thing to notice is that relative to our traditional model of how we would use our storage systems, like for example, your Facebook app or Instagram app and so on, generative AI storage requirements are very different. In particular, for traditional Instagram, if you will, there are a lot of users accessing pictures or videos or whatever. And when they access it, because it's across the world with many requests coming in, the most important part over here is it's a long, consistent stream of I/O where throughput of this data, how fast you're getting, is very important. In Gen AI, generative AI model training, we get very bursty I/O traffic. So the checkpoint is not a continuous stream, right? You have bursts of checkpoints or bursts of data ingestion that are happening. And here the throughput is not the most important part. The latency is the most important part. But more importantly is the P99 latency. Who is the last person who got the data that they need? That's the most important part, because it's synchronous training, which means till the last person gets their last byte of data, no one can start computing. Okay, so the max latency is what matters the most for generative AI training. Again, relative to our traditional applications, where storage is a very expensive part, for Gen AI training, storage is a cheap part. Okay, so well, it's not cheap as such. When we're actually looking at the cost, we are using flash storage everywhere. We thought the cost was actually pretty high for flash storage for these systems. But then we compared that against the GPU price, and then we thought, okay, this is not too bad, relatively speaking. Okay, we'll evaluate a lot of external options for our storage systems, but I won't talk about all the vendors we evaluated, but we had two main, both hardware and software vendors, but we had two main constraints that essentially stopped us from using most of the vendor solutions. One was it needs to work at scale. Okay, a lot of vendor solutions are not as scalable to these large number of GPU systems. So that was a big blocker. The second, probably even bigger blocker, is many vendor solutions didn't meet the privacy and security standards that Meta has. Now that's a big no-no for us. Okay, if they don't meet the privacy standard, then it does not matter how good the solution is. It could be the most brilliant solution in the world. We still can't use it because the privacy and security is almost foundational. We can't accept a solution that doesn't meet those criteria. Based on these, a lot of vendor solutions had to be discarded, and we had to essentially build in-house our storage and file system. Because we were building in-house, we couldn't have all of the fancy bells and whistles for what a traditional file system would look like, but it was enough for our use case. We had highly scalable, a big file, sort of high throughput file system. It had very simple semantics. It only had append semantics, which is fine for checkpointing. It didn't have, you can't go and edit a previously written part of the data, which was fine for our use case. It didn't have NFS look and feel, which was also fine, because we control the entire end-to-end stack, all the way from the model down to the trainer stack, the PyTorch stack, the communication libraries, the file system, everything is meta-developed. So we could go and modify this. It's okay if it doesn't provide traditional NFS look and feel. We can work around that in our applications. One thing to point out, as I mentioned earlier, is that because we are very sensitive to the max latency, not the average latency, we had to do very careful analysis to figure out how we would do this sort of thing. You can see the top two graphs on the top right. If you don't have generative AI content, if you're looking at regular content, the P99 latencies are pretty good, less than 20 milliseconds, well below 20 milliseconds. But the moment you add this bursty traffic from generative AI, because of these bursts, while on average we are doing fine, our worst case latency becomes very high. So we essentially built a lot of techniques around this, both software techniques and hardware techniques. In fact, we built a fully dedicated storage system just for our Gen AI workloads. As I said, even though it's all flash storage, even though it's expensive, relative to the total cost of the system, relative to the GPU cost, the overall storage was on the cheaper side. So we felt that the cost difference in building out a flash-based dedicated storage system was not significantly larger for the overall system. Okay, that's with respect to the data and storage system. Let's switch gears, talk a little bit about, I'm doing on time, 25. Okay, let's talk a little bit about our network architecture. On the network system side, we have a very large infrastructure that spans multiple areas, multiple units of computation. We have racks of computation. Each rack has 2 nodes and a switch called as a top of rack switch. It's actually not at the top of the rack, it's in the middle of the rack, but it's called a top of a rack switch. And then these switches connect to a core switches in the back end. And this unit, the one you can see at the bottom left corner, that unit is what we call as an AI zone. And now this is a full bisection bandwidth unit of computation. And we have many of these units. Each of these units is about 4,000 GPUs. We have many of these units all connected together through a higher level switching infrastructure, which is tapered to a 7:1 tapering ratio. That's the overall supercomputer that builds a 24,000 GPU system. Now, getting performance at scale and these sort of systems is not easy. If you have not read this paper, I would recommend reading this. It's Torsten's paper called Multi-Stage Networks Are Not Crossbars. I think it's like a 20-year-old paper, but it's a very good paper. I would recommend reading that. Basically, what it says is that if you have a crossbar and you have processes, GPUs communicating across that, you can get full bisection bandwidth over there, fully non-blocking paths for this communication. However, if you have a fat tree sort of network, there exists a set of paths which are fully non-blocking, but not all paths are fully non-blocking. Okay? So if you're doing, without a global planning, if you're doing communication, you could have route conflicts, you could have route contention. And that's what we see in practice. In fact, a bunch of algorithms you are show on the right, if you're doing, let's say, a simple collective, like an all-gather operation, you can do it in many ways. You can do direct communication between all the processes, you can build a tree sort of network, or you can have a linear ring sort of system. And all of these, like, if you think about as like academically, right, I would always want to do a full mesh. Why will I want to do a ring? Why will I want to do a tree? Right? Why will I add more latency to my system? What happens is that if I do this fully congested ring, fully congested mesh sort of communication, I have too many route conflicts on my fat tree because it's not really a fully non-blocking system. That makes it very hard for us to get final good performance out of the system. So we had to work around these in our production systems. And someone at Meta had quoted this. I put it on my slide over here. In production, networks rarely are well behaved. What we typically refer to as corner cases in academic conferences, these are not corner cases. These are really front and center. This is what we see every day. These are not really like once in a while that happen to us. So these sort of things become very important for us. Here's an example of what it looks from a static routing perspective. So let's say I have built a routing model where I have two servers, server 1 and server 2 on each rack. And every time I need to go to an odd numbered server, I go through the first half of the ports. And every time I need to go to the even number server, I go to the second half of my ports. If I build a static routing algorithm of this sort, what would end up is that if, let's say one of my servers died, there's a fault, and my job got allocated these 4 nodes over here, where 2 of the servers or 3 of the servers are odd numbered servers. Now, because of the way my static routing works, whether I communicate with server 3 or with server 5, they're all going through the same ports, causing route conflicts and congestion. This sort of problems make it very hard in practice when we have like faults, when we have reordering of nodes and so on. How to get best performance gets very hard in practice. In fact, I would challenge you to find a static routing algorithm that can work around this. It's very, very hard to come up with a static routing algorithm that can work around faults, work around congestion, and so on for all systems. Now, the obvious question in this is, why not use adaptive routing? There are all these techniques, so many papers out there that talk about adaptive routing. The big reason for adaptive routing is basically our physical infrastructure. Because of power reasons, our physical infrastructure is very spread out, very distributed. And that essentially means that we need to be able to support this system across a huge physical distance. So this is a picture of one of our data centers in Arizona. The tiny dots at the bottom that you see, those are car size, okay? So you can kind of get an idea of the scale of this infrastructure. The GPUs are spread out across this full infrastructure. And if I want to do something like adaptive routing on this scale, my network adapter needs to be able to hold packets for that long, right? So it makes it very hard to get, to be able to, amount of memory it consumes and how much bandwidth delay product it can absorb becomes very hard for these sort of very spread out physical systems. Okay, that's with respect to the network. Let's switch gears a little bit, talk about the software system over here. For the software, of course, we need to be able to scale the software for these large supercomputers, going from like few number of GPUs all the way to 24,000 GPUs. Traditionally, a lot of systems use just data parallel, where your model is replicated on each GPU, and you have the data, input data that is split across these different GPUs. We can't do that for the scale because the batch size, local batch size is roughly about, global batch size would not be large enough to be able to support this scale of GPUs. So we should be able to do more than just data parallelism. We should be able to split the model itself across the number of GPUs to be able to do that. So we need both data parallelism and model parallelism to be able to scale to these systems. So for Llama 3, for the most part of Llama 3, we used 3-dimensional parallelism, data parallel, pipeline parallel, and tensor parallel. Towards the later stages of Llama 3, we added a 4th dimension of parallelism called context parallelism. Across these 4 dimensions of parallelism, we were able to scale all the way to these 24,000 GPUs. One thing to note is that because of these multi-dimensional parallelism, we don't know communication operation has a global picture of everything that is happening, which means we have multiple conflicting communication operations that are happening, which makes it even harder for us to get good performance. So here's a quick chart of what we have our different hyperparameters look like for our Llama training. For each configuration, for each step, we add more GPUs, we add more, change our hyperparameters. This is a subset of our run that I'm showcasing over here. Roughly speaking, the takeaway I want to mention in this slide is that we got about, this is on BF16, so our peak flops is a petaflop. So roughly speaking, we got ballpark 40% compute efficiency for our systems. That might seem very low, like why are you only getting 40% instead of like 80%, 90%, and so on. At that scale, it's very hard to get the higher efficiency than that. We are trying very hard. That is something we are working very hard for future generations of Llama to even further increase this efficiency. And if the community has ideas on how we can further improve this efficiency, we'd love to hear from you. Need for parallelism. So one thing I want to call out over here is that we have, apart from performance itself, we need parallelism for other reasons, such as memory usage. So we have the large model itself is 405 billion parameters. So if you look at the weights themselves, 405 billion parameters times BF16, that's about 810 gigabytes of memory. That's not a lot of memory usage. Unfortunately, the weights themselves are not the most memory consuming part. The temporary data that this training creates, such as activations, for example, that's most of the memory that's consumed. For example, all our transformer layers, we have 100 odd layers. Each layer is creating activations that especially for the transformer architecture, is very high. That's really what takes up most of our memory. In fact, for our 405 billion parameter model, even on 16,000, we need, just to fit the model, we need 16,000 GPUs at very high memory utilization, 60 gigabytes plus memory utilization. Beyond that, we still need a strong scale for performance and so on. So around 700 terabytes of memory is what we need, primarily because of temporary data such as activations and so on. Apart from that, we also need to be careful about the different types of parallelism and the properties of this parallelism. We use data parallelism. We use fully sharded data parallelism, or FSDP, for our data parallelism. Over here, the way it works is that the weights are all spread out across the different GPUs. For every layer, every iteration, we gather all the weights, compute activations based on the weights, and discard those weights. So we are moving a lot of data. We are moving the weights, but because it's per layer, while I'm working on the first layer, I can gather the data needed for the second layer, or third layer, or fourth layer. That allows me to overlap my computation with communication very heavily. So even though I'm moving a lot of data, I'm able to overlap the computation and communication, which makes it more efficiency friendly, if you will. On the other hand, if you look at something like tensor parallelism, it moves intermediate activations, which is much more data to move, and it's very hard to overlap that communication with computation. So it makes it one of the most difficult forms of parallelism to be able to scale to very large systems. So the TLDR I want to mention over here is that depending on the type of parallelism, we have to be very careful how we map that to our hardware. Because TP has a lot of data movement and very hard to parallelize, I have to put it on my fastest communication link, for example, on my NVLink. And FSDP or DP, because I can overlap that with computation, doesn't matter to me if it takes a little longer, so I can put it across my tapered data movement, between my AI zone units, which are tapered. So this sort of approach, we have to kind of look at what's needed for these specific levels of parallelism and how we can map it to the specific hardware. Okay, that's about Llama 3. Let me spend a few minutes giving a little bit of a look forward of what we might expect for our future generations of Llama, for Llama 4 and beyond, from an infrastructure perspective. So first of all, compute is getting very expensive, as some of you might have noticed. Starting from AlexNet, which is like the big bang of our AI revolution, then the Google Transformer paper, there's a lot of acceleration of the AI models, generative AI models that are developing. In the recent 4 years, a ton of new models got released into the market. What all of these have in common is they use a lot of GPUs, and that uses a lot of money as well. That's a total spend across the industry, and total number of GPUs. Many millions of GPUs are being bought to support these sort of very large models. In fact, in our last earning call, Zuck announced that our Llama 4 is being trained on a very large supercomputer that has more than 100,000 H100 GPUs. So kind of gives you an idea of how much this sort of training is costing for these large companies. Now, because of the cost and performance aspects of these systems, a lot of vendors, not just Meta, are investing in our own silicon. Meta is no exception. Meta is also investing in our own in-house silicon called as MTIA, stands for Meta Training and Inference Accelerator. Probably need to be more creative with our naming, but that's what it's called. And that's a picture of Zuck showing the silicon. That is something we are investing in for both for performance and cost reasons for future generations of Llama to be able to use these. Now, this also brings up the question about what happens to the previous generations of GPUs that we have already bought. So we need to start thinking about, for future generations of Llama and other models, we need to start thinking about what happens when I have a huge amount of heterogeneity in my hardware architecture. I might have some GPUs, I might have some different, either from the same vendor or different vendors, or our in-house silicon, and so on. I need to be able to think about how my training stack will look like when I have these different heterogeneous systems all patched together. I should be able to train on these sort of systems. I need to be able to deal with numerical accuracy. I need to deal with performance, reliability, and so on and so forth for these heterogeneous hardware collections of systems. And that's, of course, with respect to the compute hardware itself. Then there's a question of reliability of this hardware. Now, reliability is not great already. When we make it heterogeneous, it might become even worse in the future. Here's a snapshot from Llama 3 about how our reliability looked like. Now, Llama 3 ran for many months. This is a 54-day snapshot of the Llama 3 run. And the 54-day snapshot shows that we had 466 interruptions, 419 of those were unplanned. Roughly speaking, that's about a mean time to unplanned interruption for about 3 hours, okay, roughly speaking, for the entire system. Now, most of these were GPU-related faults. Almost 60% of these were related to GPU errors. Now, this could be hardware errors like a faulty GPU or my memory stack has a problem, or it could be software-related issues such as the driver has a bug, could be a GPU driver, could be a different driver, and so on. But roughly speaking, around 60% of those were related to either the hardware or software of the GPU. Now, there are other parts of the system that created some reliability concerns too, such as the network switch and cable were creating about 8% of faults, but much lesser relative to the GPU faults. The Llama 3 paper has a lot more detail, a full table of all the faults we were seeing in this window. That's the hard faults. That's when a GPU dies or something happens and your training job stops. That's the hard faults. That's the easy part. Then there's soft faults. This is where the GPU or your system is not quite dead, but it's like this half-dead zombie that is just kind of walking around but not quite at full speed. So this is the case, that's a harder case. This is a training system with our Llama 3 one of the days where our performance, there was a problem with the system and the performance dropped by half for a period of time before we detected this problem and fixed it and the performance went back to its original state. Now, this is a relatively easy case because if a performance drops by half, you will notice it, of course. But what happens if the performance didn't drop by half, it only dropped by 10%, or 5%, or 2%, right? So how do you manage these sort of issues? In fact, a fun story about Llama 3 was that when we were training, we had every afternoon, we use air-cooled systems, so every afternoon when the temperature outside is high, the training performance drops by about 2%. Okay, when it gets colder at night, the training performance goes back up to the original state. It was driving us crazy. We didn't know what was going on, why the performance was consistently dropping every afternoon, but eventually we figured it out. We kind of we absorbed that cost associated with that. That's with faults itself. I want to speak a little bit about the data. We are running out of data. I think we all know this. In fact, even with Llama 3 and Llama 4 that we're working on, the amount of data we are almost hitting to the end. There are some projections out there. There's a source at the bottom. By around 2028, we are expected to run out of human-created data. Okay? That's where the synthetic data becomes very important. And how we create the synthetic data becomes very important because if we use our models to create the synthetic data, we should be very careful to not introduce or amplify any bias that we might have accidentally introduced in the previous model. So that's become a very important part of it. And finally, I want to talk a little bit about power. Power is a very key basic resource like most vendors out there. Power is very important for Meta as well. Meta uses 100% renewable energy. That makes it a little harder for Meta relative to, for example, Amazon, which went and bought a nuclear power plant to power their data centers. So we spend a lot of time trying to make our systems very power efficient. So in fact, almost the bottom line performance improvement is not directly performance, but perf per watt is typically the final number that we are really looking to build out. And we use a lot of training, a lot of systems that allow us to use train or scale our training to wherever the power is available. So dealing with things like asynchronous training and so on, which helps us to be able to take the training to where the power is available rather than the other way around. Okay, sorry, I ran out of time. Some parting thoughts. Scale changes everything. Something that worked at a small scale might have no influence on what works or what doesn't work on large scales. Training and serving are very different problems. I talked mostly about training over here, but serving has its own whole new set of different challenges and problems that we need to look at. We can't just train a giant model which cannot be served efficiently. That doesn't make sense. And of course, as we move to Llama 4 and beyond, there's a lot of challenges that are coming up, and we're looking for help from the community to help us with all of this. And finally, we're looking for people to join us. Please, I'm begging you, please come join us. We're desperate. So please get involved. Thank you very much.
Thank you, Pavan, for this fantastic insight about AI and system. And I'm sure that many people will stop you after this fantastic presentation